Okay, so today we will begin with the last chapter of this semester. Okay, so we will cover several limit theorems which lays the foundation of the theory of probability. And we will introduce first several inequalities. Right? Okay. Right, and so we will talk about the Chebyshev inequalities. Okay, and we will demonstrate the weak law of large number. Okay, right, and before we write down the Chebyshev inequalities, we will prove a simpler inequality called Markov inequality. Okay. Markov inequality applied to non-negative random variables. So if x is a non-negative random variable with finite expectation E of x, then for any a greater than 0, okay, the probability that of the event that x is greater than or equal to a, okay, usually we call this as a tail probability because it tells us that that x is bigger than a, has an upper bound, which is the ratio of the expectation of x and a here. A proof of this inequality uses the indicator of the tail event. Okay, so for constant a greater than equal to 0, we let the indicator of the event. This event is that any variable x is greater than or equal to a. Okay, so as we know, this indicator has two values, 1 or 0. Okay, so if the value of the random variable at outcome omega is greater than or equal to a, then the associated indicator is equal to 1. Otherwise, it is equal to 0. Okay, for all Okay, and as we know, the indicator of an event in the sigma algebra F is a random variable. Of course, it's a discriminating variable. Now, since x is non-negative, okay, i.e. x omega is greater than equal to 0 for all omega in x. Okay, so we have that the value of one variable x at outcome omega is greater than equal to the same value times the value of the indicator. All right, because the value of the indicator is either 1 or 0. Okay, so we have this low bound, and under this event, that it is either one when this event occurs, and this event means that the value of normal variable x at omega is greater than equal to a, so that when this is equal to 1, then this value is low bounded by a. Okay, so that so this can be low bounded by a. Okay, and the indicator. Sorry. Okay, so this is inequality is true for omega in the sample space. Okay, so which means that if random variable x is greater than equal to random variable x times the indicator of this tail event, and greater than equal to a times the indicator of this tail event. Now, by proposition 7.4.b, right? Dash 1, we use dash 1 because for non-negative random variables, then we know that expectation of x will greater than equal to the expectation of a times indicator of. Okay, so we have this, and this is by linearity of expectation. This is equal to a times the expectation of the indicator of this event, and we know the expectation of the indicator of this tail event is equal to the probability of the tail event. Okay. Right. So that the probability of the tail event is this equal to the expectation of x divided by a. Okay. Any questions? Okay, now we will prove the Chebyshev inequality. Alright, so shape-shifts inequality apply to random variables with finite second moment. Okay, so if x is a random variable with finite mean and a finite variance, sigma square. A random variable which has a finite mean and a finite variance, if and only if this random variable has a finite second moment, as we proved, I think, in chapter 5 before. Okay. Alright, so if x has this one, and then for any a greater than or equal to 0, the probability of the two-sided tail event, okay, so that the deviation, okay, of the value of one variable from the mean of the one variable, all right, looks to be A, all right, so you can see here that if this is the mean, okay, and so that okay, so the shaded region here, x is greater than or equal to A. Okay, so this is mean plus A. This is mean minus A. Okay. Okay, so this actually, we know this is actually equal to probability that x is in. So which means that the value of the boundary variable is in the two tails, okay? Two tails here. And so this event has probability upper bounded by the variance of the random variable x and divided by the square of A. So this is called a shape-shift inequality. So it gives that. So if we want to know that the probability that of the value of one variable x is big in magnitude. So which means that either in this ray or in this ray, okay? Then you can see that if A becomes bigger, then the upper bound becomes lower. So you can see that eventually, when A goes to infinity, this probably go to 0, of course, right? But the upper bound gives us what is the behavior that this probability decay. Okay, and you can see that it is the square invertible, right? A square inverse of A. Okay. Right, the proof here, so that we define a mean random variable y, which is a function of x. Okay. So we define y is here. Now y is a non-negative random variable with finite mean. Okay, this mean is, so that is the so its mean is sigma square. Okay, sigma square. All right. So we have a Markov so that okay, we want to find the probability of this two-sided tail event, and we can show that the square is going to equal to a square. Okay, so we square both sides of the inequality. We still have the same. So this event is the same as this event. And now we have here. Okay, and the Markov inequality tells us that here. So here is Markov's. Okay, so this is the Markov inequality. Okay, and the lower bound here is a square. So we have a square here, and this is sigma square and a square. And we have done. Okay, so you can see shape-shift inequality is actually a direct consequence of Markov's inequality. Yeah. Now, proposition 8.2.3 in the textbook is actually the proposition 7.4.c we have proved in chapter 7. So let me state that. Let x be a random variable with finite mean. Right? And then variance of x is 0 if and only if and only if that x is equal to its mean with probability 1. Okay, and so we let y to be the difference between one variable and its mean. Okay, so y is the deviation of the one variable x from its mean, right? And proposition 7.4.c says that the second moment of y is 0 if and only if that y is 0 with probability 1. Okay. So that is exactly the statement of proposition 7.4.c there. But the second moment of y is actually the variance of x. We know that this is equal to expectation of x minus u. Okay, and so this is the variance of x. Okay, so exactly the second moment of y is actually equal to the variance of x. And y equal to 0, which means that x is equal to the expectation of x with probability 1. Okay? because y is the difference. So y is 0, means that x is equal to the expectation of x. Okay. All right, so this is exactly what we have. All right, so now we were able to prove the weak law of large number. Large numbers. Let x1, x2, be an infinite sequence of independent and identically distributed abbreviated as IID random variables. Each having finite mean equal to here, the mean. They must have the same mean because they are identically distributed. And the finite variance which is sigma square. Okay, so they must have the same variance. Okay, and then for any epsilon greater than or equal to 0, the probability that the sample mean up to n terms, so this is the sample mean minus the ensemble mean or the expectation greater than or equal to epsilon. Okay, so this probability goes to 0 as n goes to infinity. So usually we call this as the sample mean. Okay, because it's a random variable. It depends on the outcome, okay, of your random experiment. And this mean is called the ensemble mean. Okay, so this is called the ensemble mean here. Okay, so if you use the sample mean to estimate the ensemble mean, then the deviation, all right, which is bigger than epsilon, doing epsilon, you can prescribe the either. Okay, for example, you can prescribe epsilon to be 10 to the minus 5, right? For example, or you can or for example, 1%. Okay, so the deviation 1% is greater than equal to 1%. Then this event occur, right, with probability which going to 0 as n goes to infinity. So it means that this other event occur with very low probability. If the size of the sample, right, the n is big enough. Okay, so this is called a weak low or large number because it is expressed by probabilities. Now, so the proof here, for each n greater than equal to 1, we let y sub n to be the sample mean. Okay. Right, and so that now we have, so the expectation of the sample mean, okay, would be by the linearity will be because they have the same mean, so right, so the sample mean has expectation which is equal to the ensemble mean of each random variables. Okay, of course, right, and the variance of yn, so it's the variance of right, and by its n square of the variance of the sum. Okay, this is from proposition 7.4.2. Okay, and the variance of the sum of independent random variable becomes to the sum of the variance of xi. Okay, so this is from proposition 1.2. All right. But they have the same distribution, so they have the same variance. So this is n times sigma square. Okay. All right. So you see that as n go up, right, the variance of the sample mean go down. Okay. So as n is big, then this variance becomes quite small. Okay, so yn has finite expectation and a finite variance. Now we can apply, so we can from the Chebyshev. So from the Chebyshev inequality, for any action going to 0, the probability that yn minus mu greater than equal to epsilon, okay, is less than equal to sigma squared divided by n, and this is epsilon square. Okay, because the numerator is the variance of y sub n, okay? And this is the mean of y sub n. Okay, so we have that. So this is actually n. Okay. All right, and so what is that? So this is x1 plus x2 plus plus xn divided by n minus mu greater than or equal to epsilon is then equal to n. Alright, and so as n goes to infinity, okay, as n goes in the upper bound goes to 0, and probability always non-negative, right? And so that probability of goes to 0. Cool. So the weak-low large number is the direct consequences of Chebyshev inequality. Okay. So we have that. Okay, this version of weak-low large number require that the sequence of random value here, this IID sequence of random variable, have finite mean and finite variance. Okay, but the condition, so remark. All right, so due to Kinchin, okay, so Kinchin is a rational mathematician. The weak law of the large number right? The weak law of large numbers is true when x of i's are pairwise independent and identically distributed random variables with finite minimum. Okay? With finite minimums. Pairwise independent means that only if you pick up two out of random sequences, xi, xj, these two random values are independent. But if you pick up three, xi, xj, and xk, these three random variables may not be independent. Okay, so that so pairwise independent is because independent means that if you, as we defined before, a sequence of random variable is called independent. It means that if you pick up a finite number of them, right, they are independent of each other. Which means that the joint CDF of x1, x2 up to xn is equal to the product of the marginal CDFs of x1, x2, x3 up to xn. Okay, but for pairwise independent random variable, we only know that xi and xj are independent, which means that the joint CDF of xi and xj is equal to the product of the marginal CDF of xi and the marginal CDF of xj. Okay. But if we pick up 3, for example, x1, x2, and x3, then the joint CDF of x1, x2, x3 may not be equal to the product of the marginal CDFs of x1, x2, and x3. Okay. Right. So this is a much weaker condition. But we also require that this fundamental value are identically distributed. Okay. And furthermore, we don't need this fundamental value has finite variance. Only finite mean will be enough. Okay? And the reason why this version of weakly large number require finite mean and finite variance is because we use Chebyshev's inequality. Because to use Chebyshev's inequality, we require finite mean and finite variance. Okay. Right, and so Kingin's proof for this weaker condition is actually involved. So I will say, but the proof is more involved. Okay, and so I will not include it in the class lecture because we are not well prepared for such a proof. Okay. Right. But it's good to know that if you want to apply the weakly large numbers, you know that you have the weaker condition. Okay, so the condition you have is weaker, much weaker than the condition given in proposition 3.2 in theorem at 8.2.1. Okay. Any questions? Yes, please.
Why are they required to be identically distributed?
Oh, well, the good reason is here that we actually use the so-called common mean here, right? Because if they have identity distribution, then they will have the same expectation. This is the first thing you can see, okay? And the second thing is much more involved is because that with this condition that the proof will be able to be successful because that they are examples that if they have a different means, then as you know, for example, if the means of x1, x2 going up, for example, they are not constant because if they have a different distribution, then it is possible that their expectation going up and maybe going to infinity, right? It's possible. Now, so as n goes up, then the value of xn maybe become bigger and bigger. So if you take the average, then you will have some target behavior, which that this sample mean may tend to very big. And how do we write down the expectation? We may say that we may use the average of the expectation of each x of I, right? You may find that, all right? But in that case, then they there are some strange behavior you should deal with. Okay, so that is the typical reason that we keep identical disputed things. Okay. Okay, and it is possible, if you allow non-identical dispute running variable, then you should put more conditions on their means. For example, their means they have bounded the mean. Okay, so that you can define the so-called the average of the mean in a sensible way. Okay, so that is possible. That is possible. Yeah. So, okay, so you may need some more stronger conditions for the weak-low relation to be to hold. Yeah. Okay. I think the Kinshasa inversion, which is more useful, is because that it gives us a weakened condition for independence. Because the original version require that the whole sequence is an independent sequence of random variables. Okay, so this is the most stronger condition about the independence. But pairwise independence is a much weaker one. Okay. So other questions? And as you will see, if we talk about the stronger or large numbers, then you will see a version of the stronger or large numbers allow that random variable xi's have non-identical distribution. Okay. Okay, so this section we talk about the central limit theorem. Before we state and prove under certain condition, to prove the central limit theorem under certain condition, we need a lemma. Okay. So let Z1, Z2, be an infinite sequence of random variables having CDFs f sub z sub n z and Neumann generating functions. n sub v sub nt, each of which is defined on a neighborhood of the origin in R. Okay. Right, and we let Z be a random variable having CDF f sub z of z and moment generating function n sub z of t, which is defined on a neighborhood of 0. Okay. Now, if the moment generating function of z sub n goes to the moment generating function of z as n goes to infinity for all t in a neighborhood of 0. Okay. Then the CDF of Zn goes to the CDF of Z as n goes to infinity for all Z in R at which the CDF f of Z is continuous. Okay. Okay. So this lemma give us a condition by using moment generating function. Okay. So the convergence of moment generating function, okay, implies the convergence in distribution. Okay, means that the distribution function, okay, goes to of z sub n goes to the distribution function of z. Okay, as n goes to infinity for all z. So if you fix a z here such that at which this function is continuous, then that f sub zn of z goes to f sub z of little z as n goes to infinity. Okay, so So I will just state this lemma here without proof. Okay. So I will give for a proof. Press C, theorem 6.3.2 in CL Chung. So it's Kai Chung's textbook, a course in probability theory. Second edition. (1974). Right, so this is a very good textbook. So if you think that this course is the first course for you in probability theory, then that would be the second course. Okay, but before you read this, this textbook, you need at least you need advanced calculus. Okay, as a prerequisite. Okay. But you still can refer to the theorem in this textbook. Okay. So I have a state this lemma in the context, all right, as we have up to now, especially we use the moment-generating function we discussed in chapter 7. Okay. Okay, so this is actually a very good tool. If in some situation you need to prove that for a sequence of random variables that you want to know that the CDF of the sequence of random variable goes to the CDF of a certain random variable z as n goes to infinity, then this lemma just indicate that you just check whether the moment-generating function of this sub n goes to the moment-generating function of z. Okay, as n goes to infinity for all t in the neighborhood of the origin in the real line. Okay, and usually it is not hard to find the moment-generating function of the random variable z sub n you need to study. Okay, and so first of all you find that the limiting function is indeed a moment-generating function of a certain random variable z. Okay. But in today's lectures, we will use this lemma to prove the central limit theorem. So let x1, x2, etc. be an infinite sequence of independent and identically distributed random variables, each having finite mean and finite variance. Then the distribution of right? So this one is actually the normalized sum of x sub i's. Okay. Right. So this random variable, that is this random variable, tends to the standard normal distribution as n goes to infinity. That is for each a, okay, between minus infinity and infinity, the probability that this normalized okay, less than a well goes to phi a, big phi a, and this is as n goes to infinity. Okay, so as we know, x1, x2, xn, they are well, maybe I so here is a proof of theorem 8.3.1 when the moment generating function m of xi t, okay, which is at t, okay, because xi are identically disputed, so they will have the same moment generating function exists or is defined on a neighborhood of the origin in R. Okay. You know that if the moment mean function of each x of I is defined on a neighborhood of the origin, which means that this random variable x of I have moments of any order, right? So this is a very strong condition, as we studied in chapter 7. But this is not necessary, okay? Why? Because in here, we just require that this random variable has finite mean and finite variance, so that their set moment may not exist, okay? But in this case, the central limit theorem is still valid. Okay, so the statement here is the standard statement. Okay, it's the standard statement. It only requires finite mean and finite variance. Okay, but of course that the proof will be more involved. Okay, the proof is more involved. So we only are prepared for such a proof. So if the condition is stronger, as here, that the moment mean function is defined in the neighborhood, then the proof will become to be more tractable in our class lecture here. Okay, so this is the proof by assuming that the moment mean function of t is defined on the neighborhood of the origin. Okay. Now, for each n greater than equal to 1, we let the z and the normalized and the centralized, so that okay. All right. Now, so we call the z sub n is centralized and normalized. Why? Because the expectation of zn is 0. Okay? Bilinearity of the expectation. And this is equal to okay? So first of all, this is centralized and normalized random variable. G sub n has 0 mean. And how about the variance of Z sub n? Okay. The variance of Z sub n, it becomes to be so we will see here. We will do that step by step. because that is divided by this constant, so we will have the square here. And the variance of minus n mu. But to add or subtract a constant will not change the, so this is the n sigma square, will not change the variance, okay, here. And because x of r's are independent, so we have this variance of sum becomes sum of variance. So this is n sigma square. So variance is equal to 1, so that we can normalize them. Okay. Okay, so this is called the centralized and normalized sample and sum. And normalize the sum of x1, x2, partial sum of the sequence. Okay, so we call it a singularized and normalized the partial sum. Okay, so we keep the partial sum here. And you can see this is for any n, right? For n greater than 1, the expectation of Zn is 0, the variance of Zn is 1 here. Okay. Okay, so the idea to prove the single theorem is here, is that we want to show that if Z is here, then we want to show the CDF of Zn goes to the CDF of a standard number running variable Z. Okay, right? And so the CDF of the standard number running variable is actually the big phi of A here. Okay, because this is the probability density function of a standard number running variable. So that this is actually the CDF of standard number running variable C. All right? Right? So for this to be true, by applying law 8.3.1, we will show that the momentum function of the partial, centralized and normalized partial sum is 1. So the momentum function tends to the momentum function of a standard number running variable, and we know what is that exactly, right? Okay, so if we want that, so we want this is phi z. Now we need this is actually exponential function of t square, right? Here. So this is the momentum function of a standard number running variable. Okay. So this is the here, and this is the CDF of state non-rounding variable. Okay, so our job now here is to prove the moment German function of this sub n of this singularized and linearized partial sum, okay, has a limit which is the exponential function of this form. So any question about the proof strategy? All right, so now we calculate the moment generating function of this sub n x here. And so this is expectation. It's here. Okay, and by linearity of the the constant term is here, and expectation of E because x1, x2, up to xn, they are independent. So their functions are independent too. Okay, and so this is things. Okay, so you will take the function, maybe we use g, right? It will be like g before. Okay. G is an exponential function, right? So that is continuous. And so these are random variables. And because x1, x2, xn are independent, so g of x1, g of x2, up to g of xn are independent. Okay, and the expectation of the product of independent random variables is equal to is equal to the product of expectations. So this is proposition. 7.4. Okay, I forgot. 3.4.1. Okay. All right, so this is t square root of n mu divided by sigma. All right, and because that x of i's have the same distribution, so that this is n of t sigma n here, and raised to the nth power. Okay, we know n of t. Okay, this is the moment-generating function of x of i's. Alright, so the moment-generating function of this sub n can be expressed by the moment-generating function of each x sub I. Okay, and we have that here. Right now, because we have power terms, so it's quite natural to take the logarithm. And since moment-generating function are positive, so the value of moment is always positive. Okay? So we can take the natural logarithm of the n of z and t as here. So we take ln t defined to be the natural logarithm. Okay, the natural logarithm here. Alright, and so we have minus t square root of n mu divided by sigma here. Plus n, okay, the natural logarithm of n of t sigma square root of n here. Okay, and so that this is t square root of n mu divided by sigma plus n L. Alright, so define the natural logarithm of the moment-generating function of x of i's where L of t is defined to be a natural logarithm of n of t. Now, we want to know the behavior, right? So, as n goes to infinity, and you can see that as n goes to infinity here, of course this term, you know that this term will go with magnitude goes to infinity. But here, you can see that the argument goes to 0. Okay? It goes to 0 here. So, okay. Now, so we want to know the behavior. Okay? We want to know the behavior around t equals 0. Okay. Now, note that look at the natural logarithm of the momentary function of each x sub I. All right, this is 0 and 1, so it's 0. Okay, and the prime 0 here, we know it's okay. So that this is new and 1, so it's new. Okay, new here, because by the property of momentary function that n prime at t equals 0 give us the first moment. Okay. Now, how about the second derivative of L? And evaluated at t equals 0, and we know that. So this is m double prime 0 and 0 minus m prime 0 and m prime 0. Okay, and a square. Okay, and I think last night you have dealt with a problem, right, related to the logarithm of momentary function. So this is 1, so this is m double prime 0, because m0 is 1, okay, and minus m prime 0, the square. But m double prime 0 give us the second moment of xi, right? And minus the square of the first moment. And so this is the variance of xi. And so that is the variance we have. Okay. So we compute several of them. So now, we want to know the limiting behavior of the natural logarithm of the momentary function of g sub n. All right, so we get here, and this is the limit of n goes to infinity. Okay, and now here we will. Here is n, right? And we have n. So to do it properly, we divide it by the inverse of n. Okay. All right. And here we have minus t mu and the sigma. Okay. N minus 1/2 plus L t sigma square root of n here. Okay. Right? So the expression becomes here. Now, as n goes to infinity, the denominator goes to 0. The numerator, this term goes to 0. Why? Because as n goes to infinity, the argument goes to 0, and L 0 is 0. So this value goes to 0. How about the first term? The first term also goes to 0. Okay, because this is minus 1/2. Okay, so we have 0 divided by 0, right? And then, how do we do? Well, we can use the L'Hopital rule, right, in calculus. So we check the, okay. So by L'Hopital rule, the derivative would give us minus n to the minus 2. And here we have minus 2 times this one with T mu 2 sigma and N minus 3 halves and minus here. Okay, so you have here T and 2 sigma N minus 3 half L prime T sigma square root of N. Okay, so this is by L'Hopital. Rule. Okay, so this is my L'Hopital's rule here. Okay, and so we can right, and now we can cancel factors here. So this is minus n, and because when we multiply the numerator and the denominator by n to the 3 half, so we have T mu and 2 sigma minus T 2 sigma and L prime. Okay, again here. Now, as n goes to infinity, this goes to 0. And as n goes to infinity, the argument goes to 0. So L prime goes to mu here. Goes to mu here, right? By the continuity of the natural logarithm of the moment-generating function of x sub I. So now the numerator goes to 0 again. So as n goes to infinity, the numerator goes to 0, denominator goes to 0. So we apply L'Hopital rule again. Okay, so this is 1 half, and this one is a constant, so it's 0 minus, so that we have t square t square and 4 sigma square n minus 2 L double prime t sigma divided by n, again by L'Hopital's rule. Okay. Right, so we can cancel the factor here. Cancel the factor. And as n goes to infinity, so this goes to L and 0, okay? And L double prime 0 is the sigma square. So this is going to divide by 2. Okay? And because logarithm, and so that limit goes to infinity, and ZNT, which is limit exponential function of the LNT. Okay, and by community of exponential function, so this is exponential limit and goes to infinity LNT and E square. Right? So this is M of ZT, where Z is a standard normal random variable. Okay, so we have that. And by lemma 8.3.1, so the probability that approach to and we have done here. Any questions? Okay, so this limit is obtained by applying L'Hopital rule twice. Okay, twice. Okay. And we know that this is true for all t in R. For all t such that in the neighborhood, because if we say that the MT is defined on the neighborhood, say minus epsilon. Okay, so what's that? Okay, then we know that this is for all t in here, and this is for all t in epsilon. Right, so now I make a remark. The previous theorem can be proved without requiring that the non-generating function m of xit is defined on a neighborhood of the origin in R. Okay. The only requirement is that each xis has finite mean and finite variance. Okay, so we do not require non-generating function is defined on the neighborhood of the origin. And with a stronger conclusion, that the CDF of Z sub n converges to the CDF of the standard normal variable uniformly as n goes to infinity. Okay. Because the version, the conclusion here, is pointwise, means that for each A, then we have a sequence of number and goes to this number for each A. So it's pointwise, but it's indeed can be uniformly, i.e., for each epsilon greater than 0, there exists an n such that the CDF of Zn and big phi Z, right? The difference is less than epsilon for all Z in R. Okay, so that the difference is less than 0 in the whole figure. Okay, whenever n is greater than or equal to capital N. Okay, so it's here. Whenever we have a bear shape distribution, right? Okay, so this is phi Z here. And if epsilon is given, all right, so this is epsilon, and Okay, so this is phi z minus epsilon. Then you may have, oh, no, I'm sorry, this is incorrect. This is the CDF, I'm sorry. I need to plot the, I'm sorry. Okay, sorry. So this is phi z. I'm sorry. And plus epsilon so this is phi z minus epsilon. Then this is a typical okay. So that the CDF of this sub n will be within this slot. Okay, should be within for all little n greater equal to capital N there. This is called the uniform convergence. All right, so the whole function, the whole CDF converge to this CDF uniformly. Okay, so for every z in R, the difference is very small. Okay, right. So our statement, actually the conclusion is much stronger. This is called the uniform convergence, right? Not only pointwise convergence. And also we don't need the management function to be defined in a neighborhood of the origin. The only needed is that x of I has finite mean and finite variance. Okay, so this is the remark here. Okay. Okay, so not only the convergence, not only just this makes the pointwise convergence, but we actually right. Okay, and we have an extension. Now, the following theorem is an alternative version of the central limit theorem. For just independent random variables, okay, which is a special case of the Lindenberg failure. Lindenberg failure central limit theorem. Okay, the Lindenberg failure central limit theorem makes up to now is the most general form of the central limit theorem. Okay, but we just write down a special case of the Lindenberg failure central limit theorem. Okay, so this is the central limit theorem for independent random variables. So here we do not require identical distribution. Okay, we just require independent random variables. But of course, then we need other stronger condition, right? So that x likes to be an infinite sequence of independent random variables, each having finite mean. So it's each having respective finite mean I. Okay, so because they may have different distributions, so their means are different, and the finite variance sigma I square. Okay. Right, so they may have different mean and different variance because they may have different distribution. And if, right, so there are two additional requirements because now we don't have identity distribution, right? So now the x of i's are uniformly bounded. With probability 1, which means that x of I, the magnitude of x of I is less than n, okay, with probability 1. Okay, so that is bounded. Uniform bound means that the upper bound m will be the same. So they have the same upper bound. So this is called uniformly and bounded with probability 1. Okay, for all I. For some constant m greater than 0. Okay, so you see that each x of I cannot big, right? Okay, cannot big. So they should be bounded, and they have the same upper bound. So you call uniformly bounded. But this is in practice. This quite often to be satisfied, right? In our practical situation, that the random value of xi, right, satisfy this condition. And the second, the sum of the variances, so the series sum must be infinite. Okay, so the sum of their variance cannot converge, right? Otherwise, this is too small, right? All right. So the variation is not enough. So we require these two additional conditions. So if this two is true, then for each A in R, okay, as n goes to infinity of the probability of this event that summation I from 1 to n xi minus mu I, okay, divided the square root of their variance, sum of variance, square. Okay, so this is centralized and normalized sum, right? The partial sum. You can see that. Now, so you should subtract their respective means so that this is centralized. And divided by the square root of the sum of variance is going to normalize them so that this running variable always has zero mean and unit variance. Okay? And this centralized and normalized the running variable, this then equal to A. The limiter goes to the big phi A. Okay, so we have the same conclusion as our classical synonymy theorem. Okay, so this is the price we paid if identical distribution is not required. Okay, only independence among x sub I are required. Then we still need each x sub I has mean and has finite mean and finite variance. But two additional conditions are required here. Okay? Right. But this two is not very harsh. It's really mild for applications. Okay. Yeah. If your application cannot satisfy 1 and 2, then you have to go back to the Lindenberg-Fader synonymy theorem. Okay, there is a condition called the Lindenberg condition, right, to justify them. Okay, right. If you need a more general version of synonymy theorem, then you will study in the future. Then you go to Lindenberg-Fader theorem. Okay. Okay, you can find literatures on this theorem later on. Okay, so I'll stop here. Okay. And we will have a final examination next Thursday.